Okay, hey everyone, last video before the exam one. So let's try to dive into it. There's a little bit of it seems like a lot of trees here, but it's not. It's the same thing over and over again with just different contexts. So why do we care about names, first of all? Well, if you look at the taxonomy breakdown here, we have a reason, an organization of the names that follow this breakdown: domain, kingdom, phylum, class, order, family, genus, species. The trick to remember it is the Dear King Philip came over for good soup. If you remember that mnemotechnic sentence, you remember domain, kingdom, phylum, class, order, family, genus, species. The name of an organism is usually genus, species, and it's italicized the genus and species name, right? So this is the reason why we organize the living beings into those groups is due to our ancestry. So when we trace down where traits are coming, we look at the ancestry, and based on how similar organisms are together to each other, we class them in the same species if they can reproduce and make fertile offspring, or the same genus if they are from different species but really related to each other, and you go back in time in terms of relation. So the all eukaryotes, they are the domain, there's a domain of prokaryote, that's two domains on Earth, right? But then the kingdom Plantae and Animalia, fungi, you also have protists in the eukaryote domain, right? Another way to remember it, if you don't like Dear King Philip, you can remember dumb kids playing cards on three-way get smashed. A student came up with it. I thought it was pretty clever. Not PC, but pretty clever. Okay, so once we have that, we'll look at the trees. And the trees, the way we look at them is we like to use traits that are either homologous, aka ancestral traits, or derived, and those derived traits, they are only present in some places of the trees. So they're not ancestral, but to anything but the branch in which they are, right? So if a trait is early on the tree before a split, it would be an ancestral trait. Now, depending on where it is, it can be an ancestral trait to all placental mammals. Sorry, not placental mammal. That one is also to placental and marsupial, right? To that group here, but not shared with platypus, the monotrem. Whereas those dreads, mammary gland, and hair are ancestral to all species at the end of this tree. There are more species than the species we have on the tree here. Those trees are not meant to be exhaustive. They just show the species you want and the relationship between them, right? So, but remember ancestral versus derived characters or traits. Now that we have that, it's important to keep in mind the fact that those trees can be read in different ways. They all mean the same thing. All those trees here are the same. There's no difference. However, they're presented differently. So how do you make sure you keep track of like this? The fact that all those trees are saying the same thing should be an indicator that the commonalities between them is what matters. So what is common between them? You always have sister species marsupial and placental. Placental and marsupial can be flipped, but they're always the one sharing the most recent common ancestor. Right? Always, 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 always. Depending, it doesn't matter how the tree is drawn, it's always that ancestor, the common ancestor, the most recent one is between marsupial and placental, and then the next one is between monotrem and marsupial placental, right? So if you follow the order of a branching, it doesn't really matter how you flip the branches, right? It doesn't matter. So you learn something else too. You can only say that the ancestor to monotrem and marsupial and placental is older than the ancestor to marsupial and placental. You can say that. However, if there was a split here in the monotrem branch, you couldn't say which one of that ancestor and that ancestor is older, unless you have actual molecular data. We'll get back to it. It comes in play sometimes. Okay, so how do we do this? You take the species you're interested in here, for example, and you just start putting in a table their names. Well, you shouldn't put the names first. What you're going to do is you're going to use the traits. So when you look at all the remains of all the species, you're going to look at all those traits and you're going to tally which species has the traits. So light bone, three-toed foot, every species has it. So that would be the trait that's the most ancestral. And then you look at all traits that are shared with most species but one, that's the second ancestor spot. And then you continue, and if there's a trait that's shared by only two species, you know that's the most recent evolved trait. The way you then build your tree is using that information. You use, as I mentioned, the trait that is the one that's shared by everyone, and that's the first last common ancestor of all those theropods. That ancestor had light bones, three-toed foot, because everyone has that trait. That's what we know about the ancestor. And then you use the rest, and you just put the branches like that. So you see the species that didn't have the second trait, wishbones, breastbone, loss of a fourth and fifth finger. That's the one that doesn't have it. That's the species that has the base of a tree up there. And then all the other species have that common ancestor, and so on and so on and so on. Now, any trait that is only present in one species, that will be along the branch as a derived trait. There's none here, but if there are other traits that are only present in one species, they will be derived, right? So you're following the parsimony principle as we discussed before. You're making sure that you use the least amount of explanative power to show ancestry between species. Because if the traits light bone and three-toed foot were derived at the end of each of those branches, that is a lot of analogous structures when you could have just one. It would be just all about homologous structure of three-toed foot that's ancestral. Now, if only one species, sometimes it gets messy, like this is a perfect example, but sometimes one species doesn't have that trait. Well, it sounds like it could be ancestral, and that would be a derived loss here. So here what makes us use those traits, wishbone, breastbone, loss of fourth and fifth finger, as an ancestral trait to all of those, and not to everyone with the loss of all those traits there, is once again the parsimony principle. It's less, the explanative power is lesser if you need to just say those didn't have, those were not ancestral and they were derived during that branch and became ancestral to all of those guys, rather than if you say those were ancestral as well and all of those got lost here. It's more explanative power to do that this way than to do it the way that is represented on the tree here. So it's always about the parsimony principle. You can do the same thing with molecular data. So you can just exactly look at the same thing. You got all the sequences, you look how they differ from the ancestral sequence that you know, and then you look at where the difference is. If they all have a T here, right, the difference between the ancestral and all the sequence is the first mutation that happened, and so on and so on. And sometimes one of them just have a difference, as I mentioned before, that's only them that was derived. So is the G up there that was derived there, right? It's better to say that than saying A's and G's are here, and then it's G's lost here, A is lost, A is lost, and A is lost, right? It's way more costly to explain that this way. You just look at the number of changes that are required and you go with the lowest. That's the key here. So when you do that, you realize some interesting things. For example, when you look at the primate tree, at the tree here, we have what we call monophyletic, paraphyletic, and polyphyletic grouping. So let's go through those. It's really important that you understand the difference between them. A monophyletic group is called a clade. A clade is all of the ancestors. It's like the ancestor of the clade. If you go to the base of that clade, the monophyletic group here, the green, that ancestor, if you go down the branches, you go to all of the descendant of that common ancestor, and they are all in the monophyletic clade. So if you go down from that root here of that clade, monophyletic clade, every one of those is in the clade, right? So good. Now you go the other way, all the end branches of in the clade share the same common ancestor and nobody else. That common ancestor is not the common ancestor to mammals as well, or to amphibians. So if you can go down and up the tree and find your way to always the same common ancestor and always the branches that are all in the clade, it's monophyletic, one group. Now the paraphyletic group is when you go from all the tip of the branches, you see that light beige here, the reptilia, If you go for dinosaur, crocodile, lizard, and snakes and turtles, when you go up the branches, you stay in the group. So good. From the bottom of the tree, from the branches tips to the common ancestor, you stay in the group. Great. Now, when you go from the ancestor to the branches, you stay in the group, 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 or you get out of the group. So you see, one way you had to leave the group. That means you are paraphyletic. And finally, if both ways you have to leave the group, you are now polyphyletic. So the endothermic animals, if you were to make a group of only them, the pinkish one here, or purplish, if you are birds, you go from the tip and you out of a group already, because now you have a common ancestor that's not shared with mammal. To go to the common ancestor between mammals and birds, all of the endothermic animals, you have to get out of the group. And from the common ancestor to mammals and birds, when you go down the branch, you're still in the endothermic animals here, but here you get out, and back in. So when you leave the group from the common ancestor of the organisms in the group, and from the organism in the group to their common ancestor, and from their common ancestor to the tip of the branches, if you leave the group both ways, you are polyphyletic. So monophyletic, you always stay in the group from the common ancestor to the tip of the branches, or from the tip of the branches to the common ancestor. Polyphyletic, you leave the group either way, from the ancestor of the species in the group to those tips of the branches, from that common ancestor, and from the tip of the branches in the group back to a common ancestor. So when you start from the top here, you go from the common ancestor, you go to all the tips of the branches, and if you stay in the group, that's good. If you're not, you are either paraphyletic or polyphyletic. Now, when you start from the bottom of the trees, so only the birds and mammal now, because we start from the group only, and you go back up, if you go to the common ancestor that's only theirs, good. Otherwise, you paraphyletic or polyphyletic. And if both of those conditions are validated, you polyphyletic. If only one, paraphyletic. If both are confirmed, it's monophyletic. And that's pretty much it for trees. So there's no other good ways to do that but to actually train. So you're gonna have to just find species and just have fun with it, start making trees, and being able to recognize trees, being able to understand the difference between ancestral and derived characters, being able to read trees, and also being able to use the parsimony principle, and finally being able to name a clade based, a group based on its definition as monophyletic, paraphyletic, or polyphyletic, and this is where this figure comes into play. So yeah, and that's it. Good luck, everyone. Look at those videos over and over again, take notes, quiz each other. You got this. I'll see you in the next one. Bye.